In this section, we're going to talk about infinite limits. And so what that means is our function is going to be approaching infinity or negative infinity as we approach a finite value. We'll talk about limits in infinity much later on, but that's not until like chapter 3. Okay. So let's look at some examples of functions that as you approach a finite number, it approaches infinity. So think of 1 over x squared. 1 over x squared increases without bound as x approaches 0 from either side. Because even if it's like negative 0.001, close by 0, when you square it, the negative goes away. So ultimately, the limit as x approaches 0 of 1 over x squared is positive infinity. If I look at 1 over x, though, on one side, as we approach 0, it goes to negative infinity. On the other side, it goes up to positive infinity. So here, the left-handed limit of this function is negative infinity. The right-handed limit is positive infinity. So if you remember anything about rational functions, both of these have x equals 0 being a vertical asymptote. So formally, what you learned to find vertical asymptotes in pre-calc is really a limit definition. So the line x equals c is a vertical asymptote of a curve if one of the following limit statements are true. And it could be multiple of them are true, but as long as one of them is good. So if you approach c from either side, your function goes to positive infinity or negative infinity, like it did in this case. If I approach c from the left-hand side, it goes to one of the infinities, like here. When I approach from the left, I go to negative infinity. As when I approach 0 from the left, I go to negative infinity. So 0, x equals 0 is a vertical asymptote. If you approach from the right and you get plus or minus infinity, it's a vertical asymptote. These ones are definitely much harder to evaluate because you're not quite plugging stuff in, and you don't want to sit here and graph a complicated function. So instead, you've got to think about these very, very conceptually instead. So we're going to start with this problem. We're going to evaluate the limit as x approaches 4 from the right of this function. And so I'm going to think about what's happening in my numerator and denominator separately. So when x approaches 4 from the right, the numerator is approaching 12. 3 times 4 is just 12. If I'm on the right-hand side of 4, remember that means numbers that are bigger than 4. So 4.01, 4.001. X minus 4 would then be positive, but it would be very, very, very small. So the denominator is approaching a very small positive number. So I'm taking my 12 in my numerator, dividing it by a super, super tiny positive number. The quotient is going to be very large and positive. So ultimately, this limit is going to equal positive infinity. Okay. If I try the other direction, and I look at what's happening as I approach 4 from the left-hand side, my numerator is still going to 3 times 4. But since I'm approaching from the left, that's numbers like 3.9, 3.999. This is going to be a negative number in the bottom, but still very tiny. So here, when we approach 4 from the left, the numerator approaches 12, but the denominator is a very small negative number. So its quotient would be very large negative as well. So 12 divided by negative 0.00001 is a ridiculously large negative number. So ultimately, this limit would equal negative infinity. And if you were to graph this rational function, 4 is your vertical asymptote. It has the same degree, so positive 3 would be your horizontal asymptote. So this is ultimately what the graph would look like. 4 is a vertical asymptote because you have one of those limits blowing up to infinity on either side. Okay. Now, what you learned in pre-calc was you found possible vertical asymptotes by seeing where the denominator is equal to 0. But just because the denominator is 0, you may not have a vertical asymptote. It may have been a hole in the graph. So we're going to look at an example of that. Let's evaluate this particular limit as x approaches 2 of x squared minus 2 over x minus 2. Again, if we try to plug in 2, this would be 2 squared minus 4 over 2 minus 2. Gives me 4 minus 4 over 2 minus 2. We get that form 0 over 0. So I don't know what happens. So instead, let's notice some manipulation that we can do again. We can factor the top and bottom. So the top factors into x minus 2, x plus 2. Bottom, x minus 2. So those end up canceling. And I just get the limit as x approaches 2 of x plus 2. And I can just directly plug that in to get 4. So this limit ends up existing even though it caused us to divide by 0. So we don't have a vertical asymptote there. Instead, this is that removable discontinuity because you just have a hole in the graph. If you tried to graph this rational function, it would have a hole and you would graph the line x plus 2 instead and put a hole at 2, 4. Okay? So let's take a look at some properties then of these infinite limits to try to help us out. Because if you involve infinity, it's going to keep a lot of things the same if I really just add or subtract something to it. So say f of x approaches infinity as x approaches c. G of x goes to some number, 5, 10, negative 10, something along those lines. I'm going to combine these two functions. So first, if I take f of x and I add or subtract g of x, it is going to do nothing. Infinity minus 10, nothing. Infinity plus 10, still blowing up to infinity. This limit is still going to equal infinity. If I multiply these two functions, I've really got two different cases. One possibility is that g goes to something positive. The other possibility is g goes to something negative. So if I'm taking positive infinity and timesing it by a positive number, it's still going to be infinity. But if I take positive infinity and multiply it by a negative number, it's going to change that direction and go to negative infinity. Okay. And the third one is what happens when we take g of x divided by f of x. So think of this in some realistic example. You have 2 going on in the numerator, and the denominator is growing larger and larger and larger and larger and larger and larger and larger. 2 divided by a ridiculously large number would be microscopic. So as long as that denominator is going to infinity, the numerator is going to a constant, this limit is going to equal 0. Okay. And then if you change this to one-sided limits, if you put a minus or you put a plus on any of these, same idea is going to hold. Okay. So let's try some examples. Let's look at the limit as x approaches 0 of x plus 3 minus 1 over x. Okay. So the first thing we're going to do is we're going to look at the limit as x approaches 0 from the right of 1 over x, negative. So if I'm approaching from the right, that means we're picking positive values. So here's 0. We're coming in from this side, 0.1, 0.001. 1 divided by a positive number, going to be positive, but you have that minus out front. This will equal negative infinity. And then for this other piece that we have here, the x plus 3, if I take that limit as x approaches 0 from the right, this I have no problem just plugging 0 into. So this limit is equal to 3. So ultimately, I'm taking 3 and adding to it negative infinity. This limit that I'm trying to find, x plus 3 minus 1 over x, is like 3 minus infinity, so it's just going to be negative infinity. Okay. All right. Let's try looking at this one. we've got the limit as x approaches pi over 2 from the right of -2 over cosine of x. And so here I've got to dissect into the cosine graph, so I'm going to go ahead and graph it here. You want to be really comfortable with your sine and cosine graphs and evaluating these. If we approach pi over 2 from the right, it's going to 0, but it's going to be a very small negative value from this right-hand side. So we want to notice that the limit as x approaches pi over 2 from the right of cosine of x is 0. But since it's approaching from the right, it's a very small negative number. So my numerator is going to -2. My denominator is a really small negative number. Negative over negative cancels out, gives me something positive. So here the numerator approaches -2. So their quotient approaches a very large positive number. So ultimately, the limit as x approaches pi over 2 from the right of -2 over cosine of x is going to equal positive infinity. Okay. And finally, we've got one last question. We want to find the vertical asymptotes for this function, x over sine of x. And so you're still going to find vertical asymptotes just like you're used to in pre-calculus and trigonometry. Vertical asymptotes occur when that denominator is 0. So in this case, that sine of x is 0. Really, that just happens at multiples of pi, so where n is an integer. Okay? But we do have one particular case that we have to also look at. So the one thing you want to notice is that if you take the limit as x approaches 0 of x over sine of x, this is our hidden limit in disguise. So I can go ahead and rewrite it. If I take 1 and divide it by this fraction, you would multiply by the reciprocal to get this. And that bottom goes to 1. So really, there's no vertical asymptote at 0 itself. So if I try to plug in 0, that's 0 over 0, my indeterminate form. All these other ones, pi would be pi divided by 0, 2 pi divided by 0, 3 pi divided by 0, negative pi divided by 0. Every other multiple of pi causes an issue, but 0 over 0 is that problematic form. So ultimately, there's no vertical asymptote here. So only when x equals n pi, n is not 0, is an integer, those are where our vertical asymptotes are going to occur. Okay? So keep a lot of this stuff in mind. It's going to be best just practice with these, and you'll get a better hang of it, especially in stuff here, trying to think conceptually of what's going on with these kind of functions, definitely difficult. So do your best.